Okay, time to get started. So here's where we were last time. Another application of Riemann sums. So the question is, how do you find the volume between two different graphs? So for example, here is a graph of that function g. Note the equation. Here is a graph of this other function f. Two graphs, and I want to find the volume that's in between them. Now again, let me just remind you, our goal with this example is not to find the answer. Our goal with this example is to get practice recognizing how Riemann sums can help us analyze questions. Right? So we want to recognize the Riemann sum that directly, intrinsically applies to this question. And there's a nice way to do that, and that is to recognize that if I were to take this this volume that we're trying to compute, that volume in there, and if I were to slice like this, and then subsequently also slice like this, right? So sort of vertical slices in both different directions, if you will. Then I get a bunch of little French fries, I like to call them. Right? Tall, skinny little pieces of volume. And those tall, skinny little pieces of volume have a pretty easy formula for how to, how much volume is in there. Namely, its height. Easy formula for the height. The height is this z-coordinate minus that z-coordinate. In other words, it's g minus f. Right? So the volume that we were interested in is that height times the area of the base of this shape. Oh, I guess I'll stick with the pen here. And the base of that thing, well, it's the same as the area, continuing the slicing downward, the area of this little slice of the shadow. Right? So this solid that we're actually interested in has this shadow. Imagine the sun at noon, right? Projecting straight down a shadow. That shadow down there I can think of as a domain that I'm chopping up into little pieces of area. And area of that shadow times the height, g minus f, gives me the volume. And I just want to know for each little piece of that domain down at the bottom, there is a corresponding little French fry sitting up above that, and I want to add up all of those individual volumes. Okay. All right. Now, one thing that does bother students sometimes when they first see an example like this, and that is, doesn't the thing, doesn't it have to touch down there? And let me just remind you, no, it absolutely does not. All a double integral is a Riemann sum. Just, for a piece of area, I just need to associate to each little subrectangle, I need to associate an expression, an algebraic expression of this form. That's it. Any expression of that form it makes a Riemann sum, namely a double integral. And the thing that I want to compute, it's a bunch of stuff up here. Right? Doesn't physically touch that little piece of area, that little red splotch of area down on the domain. But so what? I'm interested in adding up the green things. Those green things don't need to touch. Right? The green things are computed by a little formula. That formula I can add up. That makes a Riemann sum. So be it. Okay. All right. Here's an example. Suppose you want to find the volume sitting over the unit disk. Now here's our unit disk down here. Sitting over the unit disk between the following two surfaces. This surface up here, which is hard to draw, and this surface down here, also kind of hard to draw. Now we do have one worry, and that is my picture reasonably accurate here? You'll notice that in this formula, height, it is important to make sure that you have the larger z value minus the lesser z value. Higher minus lower. Otherwise, you're not writing down height. You're writing down the negative of the height, and the negative of the height is not the same as the height. And you're not computing volume. You're computing some other I don't even know what that is thing. So how do I know that in fact the green surface always sits above the blue surface? There's a couple different ways to see this. One observation to make is that because we are sitting over the unit disk, I know that x is never outside of between -1 and 1. Right, so this green surface never dips below 2. Right, likewise, this blue surface never makes it above 1. Right, so if green is above 2 and blue is below 1, clearly green is above blue. So that resolves that question, and we can proceed. And here's the formula. The green minus the blue z coordinates. Z minus z gives you that height. There's your double integral, and off you go. Now, computing this double integral is a bummer right now. Look what the corresponding iterated integral is, and it doesn't. I guess it doesn't look horribly bad at a glance. But let's just kind of try to see where this is going. Let's look at the first integral that we're going to have to do. We're going to have a y squared that we're doing an integral dy, an antiderivative dy. We're going to have a y cubed, and into that y cubed, we're going to be plugging square roots into a cube. And that's going to give us give me 2 seconds, that's going to give us a fairly unappealing function of x that I will then have to find an antiderivative of with respect to x. So this is looking pretty stinky, right? So granted, right? I'm not saying this makes the problem that we were looking at easy, but it does at least give us a foot in the door. And then I am going to recognize, I'll get to you in just a moment, but I am going to recognize that it turns out there is a better way to compute these kinds of iterated integrals. I don't want to talk about it now. It's too much ahead of where we are. We need to build up some more tools first. But there is a much better and more efficient way to. Turns out this integral is actually not so bad with future methods. Yeah, you had a question.
Why are the limits of integration negative root 1/10?
Oh yeah, so we've got to take this domain here and play the usual game. That domain, which I've drawn over here for sort of ease of just kind of reference. Here we go, usual game. What is the range of values of x? Well, x, there's sort of the first point, there's the last point. X goes from -1 to 1. Right, now let's fix for a given value of x, with that now fixed, we ask what is the range of values of y? Well, y is going to start there and end there. Those points are determined by a curve that has an equation in which you can solve for y, right? And if you write down the equation of that curve, keep in mind it's the unit disk. And if you, as required, solve for y, where am I going? I missed. You solve for y, you get those two values. Yeah. Okay. Yeah. Okay. Last observation I wanted to make about this. I mean, arguably the hardest thing about this question is drawing the picture, right? Doesn't that look like a hard thing to draw? I mean, it's one thing to talk. It's not that bad to draw a sort of a parabolic cylinder, I guess you'd call that. By the way, think back to chapter 12. How would you analyze what that surface looks like? Think about its cross. It has no rotational symmetries, but analyze its cross section. It has really nice cross sections perpendicular to the y-axis. They're all parabolas, right? But anyway, it's not that bad to draw a parabolic cylinder. What is hard is to draw how that parabolic cylinder intersects with this circular cylinder going up that way, right? That's a curved thing intersecting another curved thing. And it's artistically challenging. I encourage you to practice these kinds of things. Practice really does help in drawing three-dimensional figures. And let me point out also, these three-dimensional figures, very often, they're really necessary. They're really important. There's a temptation for some students to say, I'm an algebraic kind of person. I'm just not good with the geometry. Show me the path through multivariable calculus that doesn't require sort of visualizing things three-dimensionally. It's not a thing. There is no such. This is an intrinsically geometric class, right? So if you are not good at drawing or visualizing in 3 dimensions, then this is something you got to get good at. It's going to require some practice, and so definitely something you want to spend some time with. I am very happy to give you all my little discussion in office hours of how to draw well in 3 dimensions. I think there's some nice little tricks that if you know, if you've seen, and if you've practiced, that will really help. Right? But even knowing the little tricks, it remains that practice is important. So anyway, make sure to have a plan for how you're going to get better at drawing 3-dimensionally, and coming to my office hours and asking me for my spiel would be a good start. So anyway, I think that's an important point. That said, let me note that as hard as this is to draw, in this case, we actually don't even need to draw that picture, because we already have a generic picture of some surface sitting up above some other surface. We already have an analysis from that picture of how to compute volumes as a double integral, and notice all we did is plug in to that. Right? Really, in this problem, the only picture we really need to draw is arguably this picture of the unit disk to help us figure out what these bounds are on the resulting iterated integral. Didn't, in this case, actually really need that picture. Sometimes stuff works out nicely. Anyway, in general, you won't always get this lucky. And so, again, I do think it's a really important idea to make sure you're good at drawing. I've already given that speech. But anyway, notice in this picture you don't. Okay, here's another example. Sometimes the domain is not given. So this is a nice example of that. Let's find the volume that's stuck in between these two surfaces. Now again, there's only one such volume that's really truly between these surfaces, bounded between these surfaces. Maybe I should have said bounded. Anyway, here's the surfaces. That surface we know is a paraboloid. This surface we know is a plane. I appeal to your geometric visualization skills. If you take this paraboloid and you take a planar slice cut through that and ask, what's actually bounded in between there, well, it's this right there. Okay, so how would I find that volume? No domain given. Right? So the idea of this question, we already know the formula is, z coordinate of the top surface minus the coordinate of the bottom surface, do a double integral. Right? The big question is, what is the domain? Okay, here's the way you break this down. The domain is the shadow down here. How do I understand the shadow? Well, the shadow is what's bounded by this edge. Where does that edge come from? That edge is the shadow of this, what you might call edge up there. What is that edge? That's where the two surfaces intersect. Let me say that a little bit differently. What we are interested in there is we are interested in points down here. Oh, I used the wrong color. I'm interested in points down here such that if you look at the z-coordinate you get from the paraboloid, and if you look at the z-coordinate that you get from the plane, I'd like to identify where are the points, where are these values of x and y, where those give me the same height. I want points, x comma y, where the height of the plane above it is the same as the height of the paraboloid above it. You see what I'm talking about? To say that differently, then, what I want to know is where is z1 equal to z2. So you're going to solve for z in both of those equations, set those equal, like so. And off you go. A little bit of algebra. Now you've got to make sure you're good at algebra 2. Make sure you're good at completing the square, for example. This is one of those situations where having memorized the quadratic equation doesn't cut it. right? You didn't have to know how to complete the square. And as it turns out, after completing the square, here's your equation. And then you can, again, invoke your Algebra 2 skills. Hey, that's a circle. How about that, right? And then you can draw that picture of the domain, the slice, and find the bounds and all the usual ways. At this point, it becomes a practice problem, not unlike ones we've already done. So I'm going to cut it here and let y'all fill in the blanks. Yeah?
For the height, we would use the height of the plane.
Use the what?
We would use the plane as like fx1.
So the height is z. Right, so the point here is, you got to. There's a point to be very careful about. An equation is not a height. An equation is a statement. An equation says that this thing is equal to that thing. So, for example, this is not a height. That's part of a statement that helps me describe a plane on which I'm interested in the height of certain points. But that is not a height, right? And certainly 7 is not a height. Right? So, importantly, the height here, these heights that on the plane, drawing this in blue, the height is z. See what I'm saying? Yeah, so you got to solve for that z. By the way, this is a very common mistake that students make, ultra common. I see this on exams all the time, that students will say, okay, well, I want to know where these two things intersect, and so I need both of these equations to hold, and so I guess I am supposed to set x squared plus y squared equal to that, I guess. I want the two things to be equal, so things should equal other things, and I don't know, that's the most interesting looking thing in the first equation, and that's the most interesting looking thing in the second equation. I don't know. It's a symbolically suggestive, but mathematically meaningless first step. Right? Very, very common for students to do this. So the way to avoid this tragic error, and of course if you write that down, you get a absolutely garbage answer. The way to avoid this is to, again, think through what you're actually talking about. I want this height here. I want the height up to the plane, namely that z, which I can solve for. That's just algebra solve for z. I want that z equal to the height up to the paraboloid, namely this z, and that's something you can solve for. Now there's a meaningful statement. I want these two things down here to be equal because both of those represent two different formulas for z that I specifically need to be equal, because that's what it means for those surfaces to intersect. Yeah.
So then which f of xy do you put in the double integral?
I don't know what f of xy you're talking about.
Like, what? The part of the double integral that means an actual equation? Or, like...
Oh, you're wondering about the integrand.
Yeah, the integrand.
Oh, okay. Yeah. So the integrand is this. It's always g minus f. Right? So so top value of z minus bottom value of z. So you got to look at the picture and ask which one of these is for these values of x and y, right? Which one of these surfaces is on top and which one of these surfaces is on the bottom. Sitting over that piece, that's the z that's on top, right? Does that make sense? That's the top surface, right? And then this, I'm just going to do it like that. That z is the bottom. So blue z minus green z. Yeah. Okay. Alrighty. I think this is a really interesting example because, again, it does require students to do some interpretation. By the way, let me also observe. I've made the observation before. I can't remember if this was in class or in office hours, but there are a lot of high school multivariable calculus classes that are very weak, and in which students are very often sort of given a very narrow, very simple collection of examples to work out, where you don't really have to understand what's going on. You can just kind of play this game that I was making fun of earlier, where you just take the algebraic expression that looks most interesting, and that you can reasonably guess where that fits in with your double integral. And you see that would crash and burn miserably here. Miserably. Right? So it is very important. Don't just kind of guess based on experience with how the symbols tend to move around, right, as to what your double integral should look like. You've got to draw a picture, make sense out of it, understand what's actually going on, and then write down the reasonable starting point, and then conclude how it works out. All right, moving along. Okay, here's another theorem I'd like to talk about. By the way, this one's not in the book very much. I think they may mention it in passing, but it's I think really terribly undersold, underemphasized for my preferences. I'll tell you why in a little while after we get this done. So there's this is a flashback to an old theorem from single variable calculus. I hope you all have seen this. If you're looking at an integral that looks like this, specifically where the domain is symmetric, so from negative a to positive a, right? And if your function has this feature of being odd, y'all remember odd functions and even functions? So an odd function, when you plug in the negative input value, you get a correspondingly negative output value. They call this an odd function because odd powers of x all have this property. Okay. So, neat theorem, such integrals always 0. Isn't that nice? Well, that just saved us loads of work, right? I didn't have to do an antiderivative. Those can be hard. Not always. Certainly sometimes they're really hard. So being able to avoid an antiderivative, hey, neat trick, right? Valuable theorem. Okay. Why does this work? Well, there's different ways to come at this. There's a point of view about substitutions. I'm going to come back and talk about a multivariable version of that later, but not now. It's for a later talk. The way I want to see this is from the point of view of Riemann sums. Here's a Riemann sum that represents the question. Here is a value of x and a then, corresponding its negative value of x. Here's what it looks like for the function to be odd. The value of the function there is the negative of the value of the function there, or vice versa. Okay. And now let's just look at the two terms in the Riemann sum. By the way, I emphasize I'm drawing a picture here just because it's kind of nice to have a picture to look at. I emphasize that we're computing the Riemann sum. The area is just a visual comfort. Right? What we're actually interested in is the Riemann sum. So let's look at these two corresponding terms in the Riemann sum. The term in the Riemann sum corresponding to that piece, whoops, I circled the wrong one, is that. Right? The term in the Riemann sum corresponding to this piece is this. There are therefore two terms in the Riemann sum which, because of the oddness of the function, are negatives of each other. Therefore, those two terms in the Riemann sum cancel. Poof, puff of smoke, right? And notice, because this is a symmetric domain, every term has a corresponding buddy term over on the other side with which it cancels. So this Riemann sum, every term cancels. Nothing's left. The Riemann sum is 0. Yep. Everybody happy? All right. So it turns out that there's a multivariable version of this. We've got to develop a little bit of stuff, but we need to develop the idea of a multivariable oddness. And we've got to develop the idea of a multivariable symmetry. And then it's going to turn out that the corresponding, the analogous theorem is true. So here we go. Comes from the idea of reflections. Here's what a reflection is. Given a line, given a point, there is a corresponding reflection of that point. I think it's pretty clear. It's the unique point such that when you make the line segment between them, that line segment's perpendicularly bisected by the original line. Or it's the point that you're looking at when you're looking in the mirror. Right, so that's the name reflection. So it's exactly the point that you would think it is. Okay, with this idea of a reflection, I can define the two notions that I need. What does it mean for a function to have odd symmetry? Let's do like this. Odd symmetry would mean that if I reflect a point, if I compare the value of the function at x to the value of the function at its reflection, I need for those values to be negatives of each other. That's what we mean by odd symmetry. That's just a multivariable version, analog of the idea we talked about on the previous page. Okay. All right. Don't make the mistake of thinking that if whatever function you're looking at, if you see an odd exponent, that function must automatically have this property. It's more complicated than that. You've really got to go through and check the algebra, and we'll do some examples in a couple minutes. The name odd is really a relic. It's sort of a holdover from when that used to make sense in the single variable setting. Don't rely on that. The exponent's odd, I'm good. May or may not be the case. We'll talk, again, examples later. Okay, what do we mean by a domain to be symmetric? Well, again, it's exactly what you would think. Symmetry means that whatever happens on one side, sort of the exact same thing has to happen on the other side. For example, something like that maybe. And the way we write that down is that a domain has the feature that whenever a point is in the set, then its reflection is also in the set. I mean, that's what the symmetry would look like. Right? Whenever a point's in the set, you need the reflection to be in the set. Whenever the point is not in the set, you need for the reflection to not be in the set. Right? Okay, so there you go. Okay. And with those definitions in mind, here's our big theorem. Big theorem. If you have a function that has odd symmetry over a line, so if your integrand has that odd symmetry over a line L, if your domain is symmetric over L, then your integral is equal to 0, which is awesome. Yeah, everybody on board? Okay, a couple of quick warnings before we go on. Do be careful. Both of these have to apply. There are so many cases where students will notice, hey, look at that domain. My domain is beautiful. It's so perfectly symmetric. Integral is 0. It doesn't work. It's not good enough for the domain to be symmetric. The function has to have odd symmetry in order to invoke this theorem. Right, so don't be too trigger happy with the symmetry theorem. It just doesn't make any sense. The argument doesn't make any sense unless the function has odd symmetry. Okay. The other thing you've got to be really, really careful about, and I've seen so many students make this mistake, these two types of symmetry have to be over the same line. It's got to be the same line. If F has odd symmetry over this line, but the domain is symmetric over that line, the argument doesn't work. It doesn't make any sense at all. And the theorem does not apply. So do be ultra careful on these 2 points. And make sure to check them. Otherwise, and again, this is one of these, I've talked about this before, and it's a dangerous scenario. That let's suppose let's suppose you apply a symmetry theorem like this when the function doesn't have odd symmetry. Then here's the problem. Nothing you've written down on the page is both true and relevant to the actual solution of that problem. Symmetry does not have anything to do with the solution of the problem at hand. What you've written down is not worth anything as pertains to showing progress in the ability to solve that problem. There's nothing to give partial credit for. Right? So this is a very dangerous theorem to use. I'm a big fan. I encourage you to use this theorem whenever it applies. Just be really careful. Watch out for that landmine. You don't want to accidentally, forgot to check that one thing, and then you get a 0 on a question. It's very dangerous. Okay, a quick argument as to why it works. I think the analogy is very strong. But imagine a symmetric domain. For example, this sort of sunfish-looking domain there. Right? You could imagine 2 different terms. We've got, let's say, the term corresponding to that piece. sitting inside of our Riemann sum. Then we've got a term corresponding to what you might call the reflection piece, right? Also inside of that same Riemann sum. It's a symmetric domain, so every little piece has a corresponding reflection piece. Because of the oddness, these two terms are negatives of each other, therefore they cancel. It's just like the single variable cancellation argument. It's just a two-dimensional picture, two-dimensional version of it, but it's morally identical. Yeah. Okay. Alrighty. By the way, you can see in this picture why it's so important that the lines be the same. Whichever line it is that gives us the symmetry that connects which two pieces that we're going to compare and try to cancel, your oddness had better be over that same line, because you need oddness over that exact line to be able to conclude that, in fact, these two pieces that pair up from the blue line actually do cancel. So if they're not the same line, then the whole thing crashes and burns. Okay, all right. So, example, suppose my domain is this unit square right there. Suppose my integrand is this function. Now there's a well-defined question, compute the double integral of this function over that domain, and I suppose one approach would be to just, slice it up in the usual way. Look at the range of values for x, look at the range of values for y, take a deep breath, plug and chug. And that would work, and it wouldn't even be that bad in this case. Look, the bounds are constants, the integrand's easy. That'd be fine, right? But again, let's think of this as an opportunity to practice using symmetry. Does this domain have any symmetries? Good news, yes. Bad news, lots of them. This domain, the unit square, is symmetric over that line. It's symmetric over that line. It's symmetric over that line. It's all symmetric over that line. Which line do you use? Well, you can use any line you want. You're just going to have to make sure that the line that you pick, over which the domain is symmetric, you've got to pick one over which the function has odd symmetry. You cannot just pick any line of symmetry of the domain. They've got to be the same line. So it turns out, as it happens in this case, this is the one to use. We use the line y equals x, and the argument as to why we use this line y equals x is because this line, you can just look and see right there what the formula is for reflection over that line. If you give me a point x comma y, and you reflect over that line, geometry argument. It's just the reflection is y comma x. You can take that formula for the reflection and you can directly compute the value of the function there. Right? And in fact, as required, the value of the function at the reflection is the negative of the value of the function at the original point. There's that oddness. Everybody on board? And now we're done. We don't have to take any antiderivatives. All I have to do is say, symmetric domain over the following line. I do have to indicate the line. The function is odd. Symmetry. Integral equals 0. End of story. Okay, yes?
Do we not have to... So, the domain is the unit square, right? But the points are outside of the...
Oh, yeah. So I looked at a picture of points outside over here to give the formula for the reflection, mostly just not to muddy up my picture. So the reflection applies to the entire plane, right?
It's not just in the domain, it could be in...
When you write down a formula for reflection, unavoidably a reflection applies to the entire plane. Yeah, so there's no particular need to draw this picture sort of, over here. It's going to be the same. It's going to be a morally equivalent picture wherever you draw it. And so again, just for sort of cleanliness, clutter, avoiding clutter purposes, I drew it sort of out of the way. Yeah. Okay, now let me tell you the rules as pertains to this class. for applying the symmetry theorem. Correction. The rules as applies to this class for exam 2, which is coming up right after spring break. It's a couple weeks away, but still. The rules are, I strongly encourage you to use symmetry theorems whenever you possibly can. I'm a big believer. Coming back to that in a moment. But here's what you have to do. What you cannot do is just say integral equals 0 by symmetry. Right? 2 reasons. First of all, if you just say integral equals 0 by symmetry, you just glossed over a lot of thoughts that are very, very relevant. Again, you've got to, this theorem only applies because of reasons. It applies because the function has odd symmetry, and that it has that symmetry over a specific line, and that the domain is symmetric over that same line, right? That's not obvious. This is a class about ideas, not answers. Right? Cannot emphasize that enough. So you've got to justify your argument. And so that's the first reason. The second reason is I am very well aware, having capitalized on the following strategy many times myself as an undergraduate, I'm very well aware that if you are working an exam and you find yourself with a double integral that you haven't started computing yet and there's 60 seconds left on the clock, I'm never going to be able to finish cranking out this integral in the next 60 seconds. Hey, throw up a Hail Mary pass. Integral equals 0 by symmetry. God, I hope that worked. Right? I have scored on that more than once as an undergraduate. The integral was, as it turned out, equal to 0 by symmetry. And that's aware as I am of that scam, I don't want to permit that scam. I feel bad about having done it myself. Right? Okay. All right. So here's the rules. You do have to tell me when you do this, such as I did in this example. You've got to specifically indicate what your line is. You don't necessarily have to give me the equation, but you have to be unambiguous about what is your line. You might say y-axis, or whatever. Maybe you give me the equation. Give me 2 seconds. So you got to tell me what the line is. You have to tell me what the formula is for reflection over that line. You then have to use that formula for reflection in making a clear argument to show that the function is in fact odd. That's what I want to see. These 3 things. Right? You got to tell me what the line is unambiguously. You got to write down an explicit formula for the reflection, and you have to directly demonstrate with the appropriate algebra that the function has odd symmetry. Final reminder: it has to be true that the domain is symmetric. You don't have to prove that algebraically. I'm very happy with you just making an assertion as long as it's true. Obviously, if it's not true, you can't invoke the theorem, right? So it's got to be true, but you don't have to give any justification. You can just assert. So please make sure to give me these things on exam 2 if you want to make a symmetry argument. I will refine these rules after exam 2. But for exam 2, you got to do this. Yes?
Can you explain again f of r above x, y?
Yeah, so that's this. That's how we define what it means for a function to have odd symmetry. Right? I need to know that if you look at a point versus its reflection, right? I need to know that the value of the function here at the value of the function at these 2 points, they have to be negatives of each other, right? So the way you confirm that this equation is true is you write down this and you compute. And you better make sure that you get what you're supposed to get. Yeah. So you got to plug in the formula for the reflection into F, compute appropriately, make sure you get what you need to get. Yeah. Right. Okay. Let me tell you why I love this theorem so much and why I'm so sort of disappointed that it's not mentioned more prominently in the book. I did a second major in physics when I was an undergrad, and no surprise, there's a lot of integrals in a physics major. A lot of y'all are engineers. Don't want to give anything away, but y'all have a lot of integrals in your future as well, right? If that wasn't already perfectly obvious. My back of the envelope estimate. It's hard to be precise. I wasn't exactly keeping track. But my back of the envelope estimate is that of all the integrals that I saw as a physics major, it's a big number, right? Large N. About 20% of them were zero by symmetry. Right? Now, there's like 9 classes in a physics major. 20% of the integrals that I had to do were zero by symmetry. That means that this theorem saved me approximately 2 full physics courses worth of integration. That's a lot of integrals, right? Massively useful, extremely useful result. And by the way, I'm not talking about little integrals like this one. I'm talking about nasty integrals that are in spherical coordinates and with sines and cosines and lots of ugliness in them. Right? So it saved me just massive amount of work. And I'd like to save you all that same amount of work. And I think it's weird that the book didn't have that same inclination. So anyway, that's my complaint there. So I think this is a really big deal. Okay, another quick example. Here's a question. Here's our domain as a triangle. We want to compute a double integral over this domain. The integrand is that. Right? How would I compute that double integral over that domain? Well, again, you can totally do this. This function's not terribly bad. Use your imagination. You can totally imagine there's a much worse integrand that maybe you would face up against instead of this one. But rather than do that, let's notice that this domain is symmetric over that line. We can easily write down the formula for reflection over the y-axis. Now, every line's different, right? Here, it's a different easy geometry that you can argue the formula for what happens when you reflect x comma y. The x-coordinate is going to be what's going to change. When you reflect over the y-axis, the x-coordinate becomes the negative of what it had otherwise been. Notice that when you reflect over the y-axis, the y-coordinate does not change. And you got to look at the picture, draw the picture, think about the geometry. You can usually just kind of write down the formula for the reflection. You always got to think it through. It's different for every line. And then finally, the function has odd symmetry because if you take this formula for the reflection that we have there, and if you compute f at the reflection, you get, as required, the negative of the otherwise f, and therefore the function has odd symmetry. The domain's symmetric over the same line. Integral is equal to 0 by symmetry. No antiderivatives, no slicing, no bounds. Much lower effort. Everybody on board? Okay. Alrighty. Now let me show you a landmine to be aware of. I've already talked about this, but let's suppose that you're looking at the same domain up here. Right? And let's suppose that your function is this, new integrand. And there's a temptation. Look, here's the temptation. It's it's clearly a symmetric domain. Y is cubed. There's an odd exponent. This function's odd. Oh, you see daylight at the end of the tunnel and you start running, right? Integral equals 0 by symmetry. You're gonna feel that urge, right? And then you just step on the landmine. And that's worth nothing in the solution of this problem because that function does not have odd symmetry over the y-axis. It just doesn't. Now let's think it through. I mean, there's the line, right? Notice that when you reflect over the y-axis, you get a negative on the x-coordinate, not the y-coordinate, the x-coordinate. And when you take that minus sign and stick it into that square, it goes away. This function over that green y-axis actually has even symmetry, not odd symmetry. Right? So beware. I put this in here because I want y'all to get this sort of experience of what do landmines look like and how can I avoid them. I want y'all to learn that in class, not on the exam. Right? So be really careful. It's very, very dangerous. Okay. All right. Okay, moving along. So there's a bunch of physics applications in this book, and I think that's great. A lot of y'all are engineers, and these are applications that you're going to eventually use. What I really enjoy doing, again, second major in physics, right? So I like talking about physics. I enjoy being able to talk about the physics motivations for the multivariable calculus that we're going to do as pertains to these examples. But we often don't have time, and this is one of those times. So good news, this is not a physics class. So why it is that certain formulas compute certain things it's really more of a physics discussion, and that's not anything you're going to be responsible for in this class, and so I'm not going to spend class time on it. Very broadly speaking, though, I want to give you a very rough idea of why these formulas work, and we want to compute here something called the centroid, or center of mass. And if you have a rod like this, right, the center of mass is where you would support it. See if I can do this. Where you would support it so that it would balance. Come on, pen. Right, so that's the center of mass. Now, how does that work? Well, the big idea is, at that point, look, the mass over here, the mass of the pen there is pulling down. And it's pulling in what we call kind of an angular fashion. It's applying what we call a torque. This pen is supported there. It's applying a torque around that way. But over here on this side, the other side of the pen is making a torque the other way. And so the center of mass is the point where the torque on this side is the same as the torque on that side. And if you write down the formula for torque and solve for this point S, and just simply require that the total torque be 0 and solve for S, here's how it turns out. And again, the rest of those details are physics, and let's not spend any time on that. So there's the formula for the center of mass, or centroid, sometimes it's called, of a one-dimensional thing. It becomes multivariable here when we look at a two-dimensional thing. And if we have a two-dimensional domain like this, right, like my little folder here, you could reasonably ask, where's the point that makes it balance? I don't think I'm going to be able to do this. Anyway, you can imagine there's a point, if I were really good at balancing things, like there'd be a point here where, oh my gosh, I did it. There we go. Right? So that's the center of mass of this thing. One way to think about where that center of mass is, that point has the feature that if I balance it on a line, the center of mass would have to be on that line, and it would likewise have to be on that line. Right? So if you simply look at one at a time, where would I put a line like that so that the torques on either side balance, solve for that number, x bar? This is what turns out to be the result. That's the x coordinate of the center of mass, and that's the notation x bar. You can make an analogous argument. Give me 2 seconds. Analogous argument. Where would you draw a line such that the torques in these two different directions balance? Solve for that thing called y bar, and there's the formula. Yeah.
Doesn't it, when you put it on a line, doesn't it, the center of mass evenly distribute on that line?
Well, so the point called the center of mass is just a point. Right? I'm just making the observation that if it balances being supported by that one point, it'll also balance when supported by additional points, including that point.
Okay.
Yeah. So in other words, if I say I'm gonna further hold it up there and there, it's not like it's going to just fall over, right? And so, but if I make the additional points the entire line, it still balances, and that gives me what I need here. Yeah. Okay. So here's what y'all need to know as pertains to Math 212. You need to know these two formulas for the x and y coordinates of the centroid, aka center of mass of a region. You have to know how to compute with this. We're going to do an example in a few seconds, and you should know what it means. And again, it's about this sort of center of support. Okay, so quick example, a lot of details. Oh, by the way, we talk about mass. Remember, mass relates to area by way of density. sometimes we're not interested in an actual physical thing. Sometimes we're just interested in a geometric figure. If that's the case, if there's no density specified, just assume the density is 1. That's just a kind of a default presumption. Okay, so suppose we're interested in this, called the upper semi-disk, radius A. Just interested in the shape, don't worry about the mass, so density is 1. Where's the centroid? So there's 2 integrals to be computed here. The x-coordinate of the centroid is determined by that integral. That will tell you, where the balance line is kind of in the x direction. Very quickly, and I'm going to be out of time momentarily, there's 2 different ways to think of it. There's 3 different ways to compute this integral. One is to brute force, right? That's an integral, double integral. Take a deep breath, slice, plow. Right, so that'd be the one way to do it. Second way to compute x bar here would be to make a physics argument. And so if you were to say, hey, look at the shape of that thing, I can think about how the physics of an actual physical semi-disk, how would that actually move? And from a physics point of view, clearly the centroid has to be on the y-axis, and therefore x bar is equal to 0. Here's the thing, that's a physics argument. This is not a physics class. That will never be my purpose in writing a question of this sort. I am not trying to teach you all physics and how to have good physics intuition. Exactly. Any such things are incidental. So what I want to see is a math argument, right? And the good news is you can still make a symmetry argument. You just have to give me the math symmetry argument. Forget about the actual solid. I want you to explain to me why this integral satisfies the requirements of the symmetry theorem that I showed you. So that integral, draw the domain, pick a line of symmetry, write down the formula for reflection, argue that the integrand in fact has odd symmetry over that same line, and then say, integral equals 0 by symmetry. Right? So that's a mathematical argument. That's what I want. Not a physics argument. Does everybody see the difference? Okay. Let me know if talk to me in office hours if you're not clear on the difference. And this is a good practice problem, by the way, for the symmetry theorem. So definitely, please take a look at that. Try to fill in those details. See y'all later. Have a good Wednesday. Go Duke.